Hi everyone, welcome to this week's CERIAS security seminar. We are very happy to have Derek Dervishian with us, who is currently a security engineer in Lockheed Martin, and most importantly, he's a Purdue alumni. So he's going to tell us about fuzzing, and I give the mic to you. Okay.
Thank you. Okay. Some water. Okay, so like previously mentioned, I'm Derek Dervishian, and we'll be talking, this presentation will be about fuzzing and understanding the landscape. And let's get into it. First, we're going to start off with the presentation. I'm going to introduce myself, and then talk a little bit about where I work, what we do, and then we're going to dive deep into the presentation itself, talk about fuzzing, the internals, how it works in practice, and some obstacles that are commonly faced during the fuzzing process. And then at the end, of course, we'll have time for some questions as well. A little bit about myself. I graduated from Purdue with an undergraduate degree in computer engineering. While I was here, I was a member of the Boilers CTF team for a few semesters, and I also was a teaching assistant for ECE 362. Some of you may have taken that class. Currently, I'm pursuing a master's in CS from Georgia Tech, part-time, while I'm also working as a cyber applied research engineer from Lockheed Martin. I've been working in this position for almost 3 years now, where my main research interests are binary analysis, reverse engineering, and vulnerability research. A little bit of info about where I work. So I work within Lockheed Martin. We have the Advanced Concepts Laboratories. That is a division of the Advanced Technology Laboratories, and this is basically a small applied R&D center within the larger Lockheed Martin Corporation. We have 2 offices in Cherry Hill, New Jersey, and another one in Arlington, Virginia. I'm based out of the New Jersey branch. Total, we have about 100 employees, most of which located in Cherry Hill. And most of the work we do is applied cyber R&D work for DoD and IC, various customers. So a little bit about why we're here. We're going to be talking to you all about an interesting and relevant cybersecurity topic that I'm sure a lot of you will find interesting, but we're also here to let everyone know we're also hiring for both interns and full-time positions. So we have some QR codes posted here, but don't worry, we'll come back to the slide at the end of the presentation once questions are taken care of. Okay. So now let's talk about fuzzing. So before we dive deep into fuzzing, let's talk about a higher level concept in program analysis. So what is it? So basically, it's a process of analyzing a program's behavior. It's mainly used for one of 2 different things: program optimization, so measuring the performance of a particular application and analyzing that, but also program correctness, which will be the focus of this talk. Which leads us to the next thing, is that there is a problem that we're trying to fix, finding vulnerability, or problem we're trying to solve. So finding vulnerabilities in software is a non-trivial task. So what are the different ways of finding these different vulnerabilities in current software? So there exists a plethora of different powerful program analysis techniques, and the technique that one might employ for a particular use case depends on a variety of different factors like program size, the format, whether or not you're looking for an automated or manual analysis, or whether you're looking for a complete or sound analysis. Yeah. Now, breaking up programming and program analysis into its 2 high-level categories, the first being static analysis. This is analysis that is performed without actually executing the program. It's highly scalable and there's high program coverage, while also having a high false positive rate. So if you were to think of someone who's manually analyzing source code, you're not actually running the code, but say you find a potential vulnerability in this code, there's no way of verifying that that vulnerability actually exists without then going ahead and finding, within actually running it and then proving that that vulnerability exists. So that might be a false positive. You may find vulnerability, but it may not be reachable or actually be vulnerable for a variety of different reasons. And we have some examples of different program analysis techniques and that are widely used in the industry and research space. But on the right hand side of the screen, we also have dynamic analysis. So this is the opposite analysis that is performed during program execution. So this typically has a low false positive rate. So if you see some sort of behavior while you're running the program, very high likelihood that that's the actual behavior that the program will exhibit. While it also has some cons of less program coverage and being less scalable, meaning that you can only execute a program with one input at a time, and you're only limited to that execution trace within the program, and you can't see anything else beyond that. And I have some examples listed below as well, one of which being fuzzing, and that will be the main topic of this talk. And we'll be diving deeper into that. So at a high level, fuzzing is an automated software testing technique, type of program analysis, like I mentioned earlier. What it basically is it's a tool that feeds invalid, unexpected, or random data to the program under test. And this program under test is then monitored for any anomalous behavior that it might exhibit while executing with this input. And the goal of this technique is to find as many bugs or vulnerabilities as possible. Fuzzers are generally able to execute the program under test many times per second, or at a very high rate in a fairly automated fashion. So that's one of its pros. Is that ability of the fuzzer. And we'll be diving a little bit deeper into fuzzing. So before we go into some of the details, let's talk a little bit about the history and how we got up to this point today. So starting back in the 1950s, computer scientist Gerald Weinberg recollected that during his time programming during the time of punch card programming, he would scour through the trash cans and find used or different punch card decks that he would use as input to test the different programs that he was programming. So that was all the way back in the 1950s. This concept of random testing originated all the way back then. Fast forward a few decades into the future, in the 1980s, some University of Texas computer science professors published a few papers on the viability of random testing as a useful testing technique. And then during that same time frame, an Apple engineer developed a tool called a Monkey, which basically simulated a bunch of different mouse clicks and keyboard presses to test the different applications for the Macintosh at the time. A few years after that, a University of Wisconsin professor, Barton Miller, while he was logged into his Unix system via dial-up phone line during a thunderstorm, he was noticing some interference, and this interference caused some of these programs to crash. So he thought that was super interesting, and that's the next semester he tasked some of his students in his operating systems course to develop a tool, in his words, called the fuzz generator, which would basically be a command line program that fed a random stream of bits to Unix utilities. And a few years later, him and his students published the results of that project, and they found that 25+% of Unix utilities crashed. They were able to get to crash. So pretty big findings there. And then fast forward to today, a lot of work has been done in the field of fuzzing. They've been applied to an increasingly diverse set of applications and environments, from different types of programs, different operating systems, different architectures. Some work has been done fuzzing CPUs for undocumented instructions, browsers, kernel, like the whole space, basically. And the main drivers for fuzzer advancement during this time has been mainly academia, industry, and the open source community. Academia, of course, researchers, professors, faculty, publishing different findings and their works on different fuzzing techniques, while industry, many companies use this use fuzzing to test their own software and also open source software. And some companies even offer fuzzing services commercially so that other companies could use these services to test their own software. And then, of course, the open source community. There have been some implementation or different fuzzing implementations that some of you may have heard of, like AFL or AFL++. Those originally started as open source projects and are widely used and widely known in the fuzzing space. Okay, so like I mentioned earlier, the need for fuzzing. So a lot of modern software, very large and very complex. To give two examples, FFmpeg and Chromium are two widely used software, have each of which have millions of lines of code, and a vulnerability in one of these pieces of software can have a pretty devastating impact if found. Just with the amount of users for each of these software projects. But given the massive size of some of these projects, it's infeasible to manually analyze these types of programs. It's very time consuming, error prone, and also fairly difficult to scale as the size of these products and applications get larger in size. It just can't mentally keep track of everything while you're analyzing a program. So we need some sort of automated analysis technique to come in and save the day, and that is fuzzing. So fuzzing tackles each of these difficulties in its own way. So fuzzing in itself can scale fairly well, produces fairly low false positives, and it's not, low initial startup time. Okay, so we talked a little bit about what fuzzing was and why fuzzing is important, but now let's talk about who actually uses fuzzing and where it actually sits in the software lifecycle. So you can see in the screen, the left-hand side, software development. So that line across the screen represents the software lifecycle, starting from when software development begins all the way to and past the software end of life. So we can see there are four main groups that use fuzzing. The software testers of a particular application, so their work mainly sits, they do a lot of testing before software is actually released, and also while the software is released to the public and up until its end of life. While the other three groups, some bug bounty hunters, industry and academia, and also malicious actors, they would mainly use fuzzing on the right side of this software lifecycle stuff, beginning when software is released all the way to and past end of life. And just a real world example, Windows 7 was released in 2009. 11 years later in 2020, Microsoft ended their support of this OS, so no more patches, no more new features. However, still millions of people use Windows 7. So obviously people want to still find bugs and vulnerabilities in that software. So you need to keep that patched and fixed. Okay, so now let's dive into fuzzing internals and how all the different components interact within a fuzzer. So we broke fuzzing up into three high-level categories: black box, gray box, and white box. On the left-hand side, black box. That's when a fuzzer has no knowledge of the program internals during fuzzing and just generates random inputs and feeds those inputs into the program under test and fuzzes that way. So this is extremely fast, but you tend to get pretty low or poor code coverage because you're just randomly testing. You have no way of knowing whether inputs you're feeding to the program, how well they're performing. On the other side of the spectrum, white box fuzzing, that is a class of fuzzing where the fuzzer has perfect knowledge of the program internals. So typically, fuzzer is able to solve path constraints and get past this difficult logic in programs to explore the program itself. However, this process can be fairly slow and less scalable than other both black box and gray box. And gray box in the middle sort of has the best of both worlds, where you're getting some lightweight feedback from code instrumentation, while you're also getting the speed of black box fuzzing. And that's where the main focus of the rest of this presentation will be, in mutational coverage guided gray box fuzzing. Okay, so in the bottom of our screen here, broke a fuzzer up into its main components and displayed it as a cycle of events that are happening from start to finish. So we can see event number 1, we have a set of input seeds. These would typically be input data that is representative of what the program under test may expect. So if you were fuzzing an image processor, input seeds may be some JPEG or PNG images, for example. So that gets fed into a seed queue. So that's a large list of different inputs. And then from that, the power scheduler selects the next seed to mutate based off of some metrics that it uses. So you have a whole list of inputs, and your fuzzer can only execute one thing at a time. So the power scheduler's job is to pick the best seed to spend fuzzing at a given moment in time. From that, an input is selected and fed to a mutator, and there you just modify that input in such a way to make it different. And then that mutated input is then fed to the executor, which executes that program with that mutated input. And as an output of that, you get some feedback, usually in the form of code coverage. So you're able to tell which execution, or you're able to tell get some information about the execution path from that program using that input. But also you have an oracle, and that gets fed back into the seed queue. If that input was found to execute a new path within a program, then your fuzzer would typically think of that input as interesting and would want to save that back into the queue, while an input that doesn't exhibit new program behavior might just get thrown away or discarded. So that's where you see the loop back of bullet or number 7, where oracle would be the mechanism of determining whether any anomalous behavior was found, and if that behavior was found while executing this program with a particular input, then that input is saved off so that an analyst could take that input, reproduce the behavior, and figure out what went wrong to fix the bug. And we'll be diving deeper into these 5 key components over the next few slides about what each one does and give some real-world examples. So first, power scheduler. Time is a valuable commodity during fuzzing. You only have limited time, and you want to find many bugs as you can in the shortest amount of time. So you want to make sure you're being efficient with what you're executing. So like I said earlier, the power scheduler's job is responsible for distributing the amount of fuzzing time among the seeds in the seed queue. So we want to prioritize the more interesting seeds and spend less time fuzzing less interesting seeds. So I used interesting a lot. What does that actually mean? It depends on your fuzzing strategy. Usually interesting and the fuzzing world relates to the input's ability to produce new code coverage or new program behavior. And then your fuzzer would think, oh, that input is interesting. I'm going to save that back into the seed queue so that I can execute it again, mutate it again, and execute it again all over again. And a real world example, so the AFL++ open source fuzzer, they let the user or the analyst select from a variety of different power schedules to use during fuzzing. One example of which is the fast power scheduler, which was implemented by a researcher in his AFL fast implementation. So yeah, this open source fuzzer gives you a bunch of options to select from, and you can choose any one of them. So next is the mutator. So we want to explore as many different execution paths as possible, and the fuzzer has to quickly and effectively create new inputs from existing ones that execute new and interesting code paths within a program. So that's the mutator's main job. Mutations can range from simple bit flips all the way to more complex structure-aware mutations, where the mutator would actually have knowledge of a particular input structure and only make specific mutations that abide by that structure, not to create any invalid inputs. For example, the AFL open source fuzzer, they have two main types of mutations, one deterministic and one havoc. So deterministic mutations range, like I said earlier, from simple additions and bit flips, while the havoc or non-deterministic mutations are things along the lines of splicing and deleting different parts of the input, trying to Okay, the next is the executor. So once you have your input and your program under test, now you want to execute them together, and you want to do that in an optimally performant manner where you're not wasting any time doing anything you're not supposed to. And performance is essential in this stage particularly. So the open source Fuzzer AFL utilizes this thing called a fork server, and what it is basically takes advantage of the fork and clone syscalls by invoking these syscalls once the execution has gotten past the initialization steps of libc and loading and things like that, so that every execution doesn't have to go through the same unnecessary step of going through these initialization procedures. And it actually, the creator of AFL found that this mechanism actually led to up to a 2x performance gain in some cases, while a different mode for fuzzing is persistent fuzzing, where you're basically taking the code that you want to execute iteratively and sticking it in a loop so that you're not incurring the overhead of the fork or clone syscalls, and you're just executing the code that you want to target within a loop. And every, say, 50 to 100 iterations, then you would create a new process just to eliminate any stale program state or anything like that. And that could lead to performance gain of up to 5x. So you have different mechanisms to speed up fuzzing in these two examples here, but that is something important to keep in mind. So feedback, what is it? So a fuzzer needs to determine the fitness of a given input seed. So how interesting is it? What is its ability to cause a program to exhibit new behavior and cause it to execute a different path within a program? So there are some metrics for that, like basic block or edge coverage, where, for example, AFL uses something called a bitmap edge coverage with counters. And for every edge, so it's a large, think of it as a large array, and each array has a corresponding edge or edge within a program. And when an edge is executed, or when a different path is executed, that path has part of that path has a corresponding entry in that map. And if that path gets executed, then that entry in the map gets incremented by 1 to indicate to the fuzzer that, oh, this new area of the program was executed. And the fuzzer will then use that knowledge and use different algorithms to analyze that and figure out what to do with that input, whether or not to save it or discard it. And finally, Oracle. So obviously, at the end of the day, we're interested in finding any anomalous behavior. So things like crashes, hangs, memory leaks. Some of these things are fairly easy or easier to detect. Like a crash would usually return a certain signal, or a hang, you can set a timeout that the program execution must finish within. But there are other things, other vulnerability types that don't necessarily always lead to crashes, but that is still of interest to software testers, finding all bugs and vulnerabilities no matter whether or not they crash. So there's these things called code sanitizers. So special compile time instrumentation that adds in checks to the program, and while you're executing the program, if any of these special checks fail, then it'll cause the program to crash, and that alerts the fuzzer, oh, this input caused the program to exhibit some bad or malicious or vulnerable behavior, and we're going to save it off so that analysts could analyze it later on. So an example of that, use after free vulnerabilities. These are dangerous vulnerabilities, but they don't often lead to program crashes, but they're still of interest to software testers that want to fix and patch these bugs. So some Google researchers about a decade ago, they implemented compile time instrumentation like I described above that checks for different memory corruption or undefined behavior or even race conditions during runtime and will alert the fuzzer or cause a crash that will alert the fuzzer that this is an interesting input and should be analyzed further. And there are some other examples below, like page heap for Windows that does some of the same thing, but during runtime doesn't require compile time instrumentation. Okay, so we talked about the main key components of fuzzing, but that's all sort of theoretical and what's ideal. But now let's get into what a real world workflow of how someone might use fuzzing in their daily lives and some obstacles they might face during this process and how to overcome these obstacles. So these are the high level steps of what someone might, these are some of the high level steps that we'll be diving deep into over the next several slides. So before you begin fuzzing, it's very important to research the program under test. So that's doing things like learning what the program does, how it operates, what are the different inputs and outputs that it's expecting, how to interact with the program, learning how to use it. So just learning as much as you can about this program, even things like trying to find maybe potentially vulnerable code within the program, whether that be manually or through a static code analyzer that searches for specific commonly known vulnerable code patterns that would alert the analyst to say, oh, this part of the code may contain vulnerabilities, and then an analyst would then be able to direct fuzzing to that area of the code, for example, or looking for any previously patched code, previous vulnerabilities, new developed code are all susceptible to remaining vulnerable even after a patch goes into effect. Patches aren't always implemented correctly and could lead to further vulnerability down the line. Next, we got to choose the right tool for the job. In this case, we're assuming fuzzing won't always be the correct program analysis technique to use when trying to find bugs and testing software, but for this case study, we're going to assume it is. There's a variety of different techniques and tools out there, like I mentioned before, and the tool or technique that you use is going to depend on a lot of the different requirements or factors that come into play when dealing with this program under test. So things like size, whether you have source code availability or just an executable, its interface, so what type of I/O are you dealing with, and just general complexity as a whole. So once you complete those two steps, you can begin getting your fuzzer set up. So initially, you just have a program under test. So one of the first things you do is usually construct the representative initial seed corpus, like I mentioned earlier. So that can contain a variety of different data, like you can just have random data, you can have valid formatted data for a particular target, like I mentioned earlier, valid images for a image processor or parser, or invalid formatted data. So you can have an input that abides by a certain structure, but the data within that structure contains invalid values, for example. So you can feed a variety of different inputs to your seed corpus that your fuzzer will then use to seed their mutations during the whole process. Once after that, you would want to instrument your program with some sort of coverage in order to be able to tell how the performance or the interestingness of the different inputs that you're executing, but also with some sanitization to detect any anomalous behavior like non-crashing inputs. Also, the execution method, sometimes depending on your program under test, it might be difficult to fuzz right out of the box, so you might have to implement something called a harness, which acts as a middleware between the fuzzer and the program under test that you would have to develop to target a specific area or interact with the program that you're trying to test. We'll talk a little bit more in detail about that later. Or if you're trying to only test a specific feature or part of the program, like a command line program, you might only want to test execution when given like a certain flag, like -A or -D. So you'd want to take that into account. Yeah, different fuzzing parameters, like I mentioned earlier. You have the ability to implement your own custom mutator, select a different power scheduler, things like that, that you want to set up earlier on. And then also fuzzing can be set up to run in a parallel mode where each fuzzer independently fuzzes the target program. And then occasionally when a fuzzer would find an interesting input, it would share that finding with the other fuzzers, and they kind of all work together in that way. So it can be run in a parallel setup like this, or it could be run in a single mode, either way. Yeah. So like I mentioned earlier, there are sometimes software testers only have executables available. So applications with source code are relatively easy to instrument with compile time, code coverage, and sanitization instrumentation. But we need to figure out a way to do that. If you're just given a binary executable, how do you insert your code coverage metrics or sanitization instrumentation into these binaries and then fuzz these instrumented and sanitized binaries? So one way of doing that is through binary rewriting. Basically the process of inserting this instrumentation into a binary without any need for recompilation. This is a typically very complicated process, and there are usually some caveats to getting it working properly. Some examples listed below of what AFL++, widely used open source fuzzer uses, these different tools, Zaffle, RetroWrite, things like that to insert instructions into the binary to add these code coverage that'll make fuzzing easier and better. And the other common way of doing this is through dynamic binary instrumentation, basically the same thing as binary rewriting, except you're doing that during runtime. Typically more stable process, but it tends to lead to worse performance compared to binary rewriting. And there are some example tools below that are commonly used for this process. Okay, so like I mentioned earlier, some fuzzing targets are difficult to interact with. Target applications like programs like network applications, browsers, GUI applications, libraries are typically hard to interact with and don't usually lend themselves as easily fuzzable targets. That's because most fuzzers are typically built for file-based fuzzing, and therefore we need to adapt these types of programs to make them more easily fuzzable. And one way of doing that is through what is called a fuzzing harness, which I mentioned earlier, acts as sort of a middleware layer between the program under test and the fuzzer. So the fuzzer is executing this middleware code, and the middleware code is then calling upon different functions, for example, within the program under test to test the program itself. So these are usually manually developed and custom developed for the program under test that you're wanting to target or test. And one example would be like something in this yellow box below, something that, for example, like opens a file, initializes the image processor, and then passes the file to the process image function, which then presumably does a bunch of parsing and processing of the image from that file. So that would be relatively simple harness that the fuzzer directly interacts with, and where the harness directly then calls upon different functions within the program under test to get around these difficult fuzzing interfaces. Okay, so that was a little bit about getting fuzzing set up. So once you begin fuzzing, now it's time to wait. Could wait for days, weeks, months. Fuzzers run indefinitely or until an analyst stops it. It's common to let fuzzers run for a really long time. Since this is an automated process, you can just let it run and go work on other things while it's running. But however, it's important to occasionally monitor the progress of the fuzzer to make sure you can fix any obstacles that you might encounter while fuzzing. And some of the obstacles we'll be talking about the next few slides are listed below. Unstable fuzzing, when the fuzzer stalls, and just general poor performance. So usually when you fuzz initially right off the bat, you'll find a lot of new code coverage within the program, and you'll maybe even find some bugs. But usually over time, your code coverage and number of bugs or crashes that you might find usually tend to saturate and level off over time. And that can become an issue. You don't want to just not find anything. You want to do something to stimulate the fuzzer and get it back on track where it's finding different execution paths within the program and have it continue on finding more bugs. So one solution around this problem would be to run a different collection, run a collection of different fuzzers on this program under test. So differences in mutators, power schedulers can show improvement and get rid of this saturation effect that we're seeing. Also, one could just stop the fuzzer and analyze the inputs the interesting inputs that it's found thus far, and manually go through and analyze these inputs to find any bottlenecks or choke points that it's running into, and then manually create or craft an input that would get around these choke points so that the fuzzer could resume and find more different program behavior. Or another option would be to even use something called a concolic fuzzer, which combines constraint solving with fuzzing. So if fuzzer reaches a difficult conditional statement that a simplistic mutator would not be able to mutate around, the constraint solving ability of the concolic fuzzer would generate an input that gets past that difficult constraint and would allow the fuzzer to resume fuzzing and finding new behavior past that bottleneck or choke point. And if all else fails, maybe just move on to a different analysis technique. Another problem that is commonly faced is fuzzer reproducibility. So a lot of times, if you're executing a program with so at the end of the day, you're saving off these inputs that cause the program crash or cause some anomalous behavior, and then an analyst wants to come back at a later time and use those same inputs to reproduce that same behavior so that it can analyze it, find the root cause, and develop a patch, for example. Sometimes these inputs aren't always reproducible, and that's a problem during this analysis phase. That's what we call instability. So for example, if you had input A, you execute it within the program, it generates an execution trace like this yellow line here, and then you take that same exact input and you execute it again right after, it might generate a slightly different execution path through the program, and that's what we're referring to as instability. Is that given the same input, it's not reproducing and giving us the same execution path within the program, and that's a problem for reproducibility. So that can be caused by a variety of different things listed here. Some of the ways around that would be to, for example, if we're using persistent fuzzing when everything is running in a loop without the program restarting and renewing its state off of every iteration. One option would be to, once a new process is created at a clean blank state, it could save all inputs sent to the program. And when an anomalous behavior is found, then it'll save off all those inputs and save it to a file so that you can feed those, replay those inputs back into the program in that same order to try to reproduce that same behavior. That's an option. Or AFL++ even offers a special compile time instrumentation to try to eliminate any concurrency issues that you might have with multi-thread behavior as well. Okay, so lastly, sometimes fuzzers just run slowly, and that's a problem because we want to find bugs as quickly as possible. And with a slow fuzzer, we don't want to wait years, months. We want to find bugs now and fix them now. So we want to solve this problem as well. Sometimes large and complex programs, long execution times are natural with a lot of just logic and lot of instructions, takes a long time to execute. One way around that is an analyst could write a specific harness for that application that only targets a specific part of the program under test. So you're not executing redundant or unimportant code, or you can utilize a technique called snapshot fuzzing, which at a certain point in the program takes a snapshot or a save of the program state at the given time during execution. And then rather at the end of the cycle, beginning execution at the beginning of the program, you begin it at that snapshot. So you're saving time by not executing redundant code during your fuzzing process. You're only focusing on the important part of the code or that you want to test. Also, complex fuzzer logic. So if you implement a custom mutator that's fairly complex, it takes a long time to execute on every iteration. That could lead to slower execution times. But also utilizing parallel fuzzing could sometimes offset and compensate for this slow performance. So that's an option as well. Okay, so once a fuzzer, say it's done running or it's still running, it's produced a bunch of results and you want to analyze these results, how do we do that? We go through the process of triage and deduplication. So you have assume you have a long list of interesting test cases that lead to anomalous behavior within the program, like a crash. So you want to triage these test cases and characterize them by root cause or vulnerability type. You also might want to deduplicate them, so remove any non-unique test cases to reduce your set, so you're not analyzing the same thing twice. Also, another step after that could be test case minimization. So that's basically the process of removing any unnecessary bytes from the input and only keeping the bytes that contribute to triggering the vulnerability or bug itself. And this could lead to an easier time for an analyst to analyze the vulnerability with a smaller input and less clutter. Okay, so that's we had there about real world fuzzing, and we're going to dive deep into some real fuzzing tools and some real world vulnerabilities that they've been used to find. So here's sort of a lay of the land of the different open source fuzzers that are currently anyone could go out and use, categorized by operating system that they're meant to run on or fuzz applications on. So under Linux, we see that we have a large set of general fuzzers, a set of directed fuzzers that are directed fuzzers basically are user or analyst is able to direct a fuzzer to only execute or try to execute a certain path or a certain area of the code and not striving for general exploration of a program. Like I said earlier, grammar-based fuzzers are given some sort of input structure, and they use that input structure when mutating new inputs. Taint-based fuzzers are able to keep track of what input bytes lead to which program behavior and can make strategic mutations based off of what inputs exhibit what behavior. And like I mentioned earlier, concolic fuzzers as well. I like to call out specifically AFL, which stands for American Fuzzy Allop. This is a fuzzer that was released in 2013 by Michael Zalewski. I think it was his own personal project that he open sourced. This fuzzer has been used to find thousands of vulnerabilities throughout the years. And a lot of these fuzzers listed here are actually extensions of AFL, just using AFL as sort of using the core of AFL and then adding on new features and new designs and new ideas on top of AFL and using AFL as kind of the core, using the core of AFL. And now AFL is no longer supported. AFL++ is now the successor that's also widely used. So yeah, basically big open source community, lots of different implementations for a lot of different use cases, no matter what it may be. But there is a lot of support for Linux-based fuzzers and some as well for Mac and Windows. Some real-world fuzzing successes like to go into the OSS Fuzz project from Google, which is a cloud-based fuzzing, which is their cloud-based fuzzing tool has found thousands of vulnerabilities over the last several years on some pretty well-known and widely used software projects. But I'd like to also point out to some of these case studies. The first one, this 2019 CVEs. A researcher used a specific fuzzer, Fuzzily, that is targeted towards JavaScript engine fuzzing to target Apple's WebKit. Prior to this, he tried fuzzing 2 other targets, but failed to find any new bugs or vulnerabilities in these targets, and moved on to targeting Apple WebKit. While fuzzing Apple WebKit, he noticed after a few days, coverage had converged, like we mentioned earlier, when a fuzzer stalls. So once this stalled, he decided to create a modified mutator to produce some other invalid types of inputs. And after a few more days of fuzzing, he got some new crashes. And during this setup, he also utilized a parallel fuzzing setup. And similar stories to the ones listed below, a lot of the things we mentioned earlier, when diving deep into the internals and the workflow, they apply to these real-world examples of people finding vulnerabilities in commonly used software in a variety of different software as well, like the following one. The 2022 researcher had to develop a custom harness to fuzz a Windows Defender, used a page heap, which we mentioned earlier is a sanitization tool to help detect any memory corruption vulnerabilities, and found a few bugs during that process as well. In conclusion, fuzzing is a pretty powerful automated program analysis technique. At the end of the day, you got to pick the right tool for the job. Fuzzing is not always going to be the right tool for the job, but if it is, you got to ensure that you're using it correctly and optimally, trying to get the most performance out of it, try to help the fuzzer get past any hard conditionals or get past any moments in time where it tends to stall. Yeah, there's a lot of open, in addition to that, there's just a lot of other research being done, a lot of it here at Purdue, a lot of professors publishing awesome research even here at Purdue, a lot of open source fuzzers available, a ton of published papers every year, articles, blogs, everything about fuzzing. So there's a lot out there, far more than I could fit in these slides here, but yeah, feel free to research the space on your own. Some sources, and then any questions?
Okay, thank you. So I was wondering, go ahead if you don't mind, use your microphone there. Just there's a button you push there. Thank you.
Okay, got it. Okay, so I was wondering, as you went through the presentation, I take it AFL++ is one of the fuzzers that you use?
Yeah, I've used it before.
When you enable it, do you have to point it to, here's the field for input, or how does it know to try and supply input?
Yeah, so yeah, that's one of the things you have to supply to it. There's a variety of different command line arguments. It's a command line tool, so there's a variety of different command line arguments. You specify the input seeds, but then in addition to all those arguments, at the end you specify, the program under test, you give it an executable, and then you give it how or what file you want to fuzz, represented by, I think, by a certain symbol that the tool will recognize to fill in with the fuzz file. So you specify there in the command line where exactly, the file should go that you want to fuzz. Yeah, I should have had an example of what sample command line looks like. But.
And another one.
Yeah.
Does it also use symbolic execution to try and find how the program runs to get to a condition to try and crash?
Does AFL++? No. AFL++ don't. They rely on just basic mutators. Mm-hmm. There are some tools like here, like QSIM is a concolic fuzzer that executes a program input, but then also does some constraint solving at the same time to try to discover new program behavior, or SimCC combined with AFL. So AFL in itself is not, but there are some existing tools out there where combine those two technologies together. And some of them are listed here.
Oh, thanks. I have another one. Running like AFL on a Unix machine, is there emulation if I want to try and have it like fuzz a Windows executable, or do we have to just use like a Windows fuzzer on a Windows binary?
Let me think. There might be a way to do some emulation with AFL that I'm not familiar with. There might be a way, but I'm not 100% sure. But there are some pretty good Windows fuzzers that you can execute. Yeah, run on Windows natively with the program under test.
Okay.
And like WinAFL, Winnie, some good options out there.
Thanks.
Yeah.
Okay, I got 4 questions from the audience online.
Okay.
Raul asks, what is the scope of implementing AI in the mutation stage of fuzzing, and can you comment on the research on this idea?
I can comment that I know that there is research in that space. However, me myself I'm not too familiar with like what exactly has been done and what exactly has been proposed in the research space. But I know for a fact that there have been some AI has been proposed to supplement different parts of the fuzzer, like you mentioned, mutators. So I'm sure if you did an easy Google search, would yield some pretty interesting papers.
Okay, VJ asks, do you think fuzzing should be included in DevOps pipelines for software companies?
Yeah, I think so. A lot of times, I guess there are 2 main ways of testing. Developers could implement specific unit tests that test specific parts of the code, but it's always good to have some other technique out there, one of which could be fuzzing, that isn't implemented by a developer and tries to just generally explore the entire space of different program behavior that a user might not know to implement a specific unit test for. So I think, yeah, to answer your question, yes.
Okay, let's see, Raul has another question. Is there a scope of implementing fuzzing in forensics? Like, can we use fuzzing while figuring out a chain of events, obtain similar checksums or digital evidence, maybe?
Can you repeat that question again? I'm trying to think.
Yeah, sure. So is there a scope of implementing fuzzing in forensics? So like trying to find like, what happened after the fact kind of thing. Like how could it be useful in forensics?
Yeah, I think yeah, I'm not 100% sure how it could be directly applied, but I think some of the general principles can be expanded off into other domains.
Okay. Let's see, we got one more from Drew. When hunting for vulnerabilities, what specifically indicates that fuzzing is the appropriate tool for the job?
Usually, I would think when you're faced with testing a fairly large and complex application, you want some sort of automated approach where the user or analyst wouldn't manually have to sift through and analyze manually a lot of this code. So an automated tool, one of which being fuzzing, I think is valuable because one, it's shown in the results that it's been able to find a lot of different vulnerabilities. Also the fact that you're actually running the program over and over again, so you're able to save off these files that an analyst would then be able to take these files, reproduce the crash, and then get right into the root cause analysis. So you have evidence of crashes right there immediately. Yeah, I'd say, yeah, larger, complex programs or projects would lend themselves well to fuzzing because manually analyzing something like that would maybe be infeasible.
Questions I see. So I guess, yeah, thanks a lot, Derek. Thank you for joining us.
Thank you.